This is a video in a series of videos where we're looking at how to compose the behavior of units. And in this video, we're going to take a look at how to add sensor models and data processor models and antenna models, which are a subclass of subsystem, to units to give the unit the ability to be able to detect other units. We're picking up where we left off in the previous video, where we have a unit that it has two models on it already. It's got a platform model and a cognition model, and the cognition model has commands in it that allow the unit to be located and moved. So I'm going to take one of these move commands off of here just to make it a little bit more simple. And we have the log output command set up. We talked about that in a previous video. So now we're going to talk about sensors and their supporting models. Before I do that, I want to go back to something that I've talked about before. I'm going to use the unit pattern to create the unit that we are actually now in the process of building up by hand. It's a shooter. So I'm just going to call this shooter and finish. So when I create a unit from a pattern, all the models that are needed by this unit to let it do whatever this unit's supposed to do are already attached. So I've got 8 different models here already attached. And some of those are cognition models, so it's got 2 cognition models on it. So if I go to the unit and go to its commands, those cognition models define a bunch of different commands. So there's the definition commands, and if I put my cursor on a line that's below the start statement, I'll have some more commands. And if I just create that unit using a pattern, I can go through here and I can read about all the different things that the cognition models that are attached to that unit can do. And I don't really have to pay any attention to the other models, the equipment models that are attached to that unit, or really the composition. In this type of unit, everything that I need to know about the unit is explained to me in the commands that are supported by the cognition models that are attached. So I don't really have to pay attention to the composition or to the models, unless I'm interested in maybe going to one of those models, say the sensor, and I might want to change its range or something like that. So I could go here and change it. But I don't have to figure out on my own when I created this unit which particular models need to be attached, because again, they are already attached. And the typical way that you create units is the way that we just did it, through a pattern. So typically the end user doesn't have to know how to attach models or which models need to be attached. So with that in mind, let's talk about the things that we've already done so far. We have added 2 models to this particular unit, and we use the employee statement for both of those. And we're going to use more employee statements to put the rest of the models on there, and then one admonition statement. As you can see, attaching a model is very trivial, and you've seen it's just a simple 2 keywords and the name of a model, 2 keywords and name of a model. So the actual process of composing a unit is pretty trivial. There's really not much to it. What makes composing a unit more challenging is knowing the combination of models that need to be attached to the unit to allow the unit to do what it's supposed to do. Because particularly all the models have certain interfaces, and they're designed to either support an interface or use an interface to communicate with other models. And you have to be familiar at least with the interfaces that the models support in order to be able to put the models on a unit in the proper combination. Usually you need to be even familiar with the internal workings of the model. And a typical end user doesn't need to know that. Typical end user doesn't know the internal workings of these models. And it's for this reason that composing a unit is usually done by the developers of the models, because it's the developers that know how the models work internally and what their interfaces are and what combination of models are supposed to be attached to a unit in order to be able to allow it to function as intended. So the developers build those patterns for units so that the end users don't need to know the details of how the models work internally. So again, the process of composing a unit is trivial, but it's not trivial to know the internal workings of the individual models. So that's the part that makes it hard. And what I'm telling you in these videos is how these particular models work. And I'm explaining how these models work as we're going through and using them to compose. Ultimately, we're going to end up with all 8 models attached to this shooter. What you're learning about how to compose will apply to any unit that you ever use, but what you're learning about these particular models will not be particularly useful because these models, as I've explained before, are not intended to be used in a particular serious scenario, serious simulation. They're here they're intentionally very, very simple so that they can be used to teach how to use flames. So what you learn about these models, it will not be tremendously helpful. In order to compose a unit with other models, you'll need to go learn about those models. And the place you'll go first, of course, is to our starter models. And we have a lot of documentation on the starter models. We've got a bunch of scenarios. We've got a bunch of unit patterns that already use those starter models. And then ultimately, of course, there's a source code to all those things, to all those models. So to really do this in its full capability to build units in there with models, you'll need to get familiar with the models that you're using. So that's a little bit of a detour. I wanted to make sure, I've talked about this already, but I wanted to make sure that was clear. And so we're going to dive in now and take a look at some of the other models that we need to attach to the blue shooter to make it look like this shooter. So I'm going to just remove that for now. And we're going to go to our blue shooter, which only has 2 models attached to it. And we're going to attach a sensor model in its supporting models. So let's talk a little bit about sensor models. In Flames, in the real world, in order to detect other things around you, you have to have some kind of a sensor. So even your ears would be considered a sensor. Your eyes would be considered a sensor. If you were doing smells, you'd have your nose would be a sensor. If you're in some sort of a military system, you're going to have a radar or sonar or an infrared sensor. We find out about the things around us through some sort of a device that is able to detect things around us. So in Flames, we model sensors because in the real world, there are sensors there. And with this, I need to introduce another concept that's very important when you're in simulation in general and in Flames in particular, and it's the concept of perceived truth. In the real world, we really never really know absolute truth about the things around us. We have sensors that are sensing the things around us, and those sensors are giving us a picture of what's around us, but those sensors could be inaccurate. They could give us false information. They could miss things that are there or tell us that there's something there when there really isn't. So in a real battle, a human operator is always operating on his own individual perception of what's going on in the world around him. And in general, perception is formed, the data that we have that forms our perception of the world around us. Perception is formed by our own local sensing capability and the information that is sent to us via communication systems from other entities or other participants in the battle that are telling us what they see. So, for example, if I'm in a surface-to-air missile site, I may have a radar that is able to detect the aircraft that are flying over me, but I also may have a communication device that allows me to communicate with other systems that also have radars, so I can see on my own local area picture of what's going on. I can see not only what my own sensor sees, but I can see what other sensors see. if I'm a human, I've got my own eyes and I can see, but I may have a radio that I can talk to the guys on the other side of the hill, and they can tell me that they just saw 3 trucks and they're coming my way. So I have in my own perception now what I'd be able to see with my own eyes plus what the guy on the radio told me. There's a lot in a simulation, if you want to have perception, you have to model it. You have to do things extra to be able to form that perception. Because in a simulation, you also have access to the absolute truth. So you can just look up in a data structure someplace, what's the true location in the simulation of this truck or these airplanes. And you could actually cheat. You could just forget about sensors. You could forget about communication devices. And you could just go look at the true position of things and then make your engagement decisions and your tactical decisions based upon what you see from the true position of where things are located. If you do that, if you allow your decision-making processes to have direct access to the true positions and states of the other units in the scenario, you are dramatically affecting the realism of the scenario, because your decision-making processes are being provided with data that does not realistically represent the data that's available in the real world. In the real world, you wouldn't know that there's 15 aircraft coming 100 miles away because you wouldn't have access to it. You wouldn't have any sensors that could see it, or those aircraft may be flying really low, below where your sensors are able to see, et cetera, et cetera. I think you get the point. So in order to allow realistic processes to be simulated and ultimately realistic outcomes to be simulated, you have to start with providing realistic inputs to all of your decision-making processes. And that all starts with sensors. There's a lot of simulations that don't model sensing all that well. They just allow things to go out to the truth and gather up that information without looking at sensors, without looking at the radar cross-section of vehicles, without looking at terrain, without looking at the ranges and capabilities of the sensor or the antennas. They also often don't play communications. There's a lot of simulations that don't play communications. They just assume that information that is gathered by one unit is just automatically available to the information that's to any other unit. Or they do some kind of thing like they put I heard of one simulation where they tried to create this object called perceived truth. And it was a central place where perceptions of all the players was managed. And you really can't, there is no such thing in the real world as perceived truth. And we're talking about real world systems here and real world processes. And there is no such thing in the real world as this central place where everybody's minds are melded together to store perceived truth. So you're absolutely going to affect the realism of your simulation if you try to have such an object. In the real world, perception is in the mind of every single participant in the battle. Every participant has their own unique perception of the world. And again, it's formed by their own local sensing capability and their communication with other units, other participants in the battle. So in order to model that realistically and hence create a simulation that can produce realistic results, you have to model the processes of forming perception accurately. And you have to allow every participant in the battle to have their own unique perception of the world around them. So that's another reason why cognition models in flames are so important. Cognition models are the places, are the individual brains of all of the humans in the battle. And cognition models store the unique perception for each participant in the battle. And the data that is stored, again, comes from the local sensing capability of each unit and the communication capabilities, so what that unit can send. So we're going to talk about communication later, but we're going to talk about sensors and local sensing capability now. Now, the individual sensors themselves, the sensor models, they are, for the reasons I've just described, they are very important, and a very important part of the way that you simulate things in flames. And I've said this before, but I just got to keep reminding you about this. You don't have to do it this way. We've defined the class hierarchies. We put all this stuff in place so that you can build simulations that can produce realistic results. But you can skip all this. You could write platform models that go directly to ground truth and make their own decisions and skip all the sensor stuff. But we don't recommend that. Well, I'm not going to teach you how to do it that way. The models that we have built make use of all the features and flames that allow you to create realistic scenarios. Sensor models are about the only kind of model in flames that is allowed to go to ground truth, go to the true position of things. Sensor models go out and look at where things are really located, and then based upon the capabilities, the performance capabilities and effectiveness of the sensors, that the algorithms in the sensor models determine what that sensor would really be able to see in the real world. And even if the algorithms inside your sensor model are relatively simplistic, it still is a useful process, a useful step to go through and let the sensor models limit what they can see, and then allow the results of detection processes to be fed to the cognition models rather than allowing the cognition models to go directly to the true positions. So that's the overall flow. Sensor models go out and they do mathematical calculations to figure out what would this particular type of sensor in the real world really be able to see. And that can be done very accurately with ground clutter and multipath and all kinds of stuff like that. Or it could be done very simply, as is done in this particular sensor model that we're going to look at. It's just a pure geometry with terrain that we consider. Sensor models gather that data up that they can see, and from that they will usually form a track. So the sensor will detect that something's there, and usually it's a periodic detection. And then based on that, some processing takes place, and it's usually takes place over time that allows the sensor to determine that, hey, there's actually something there. It wasn't just some kind of a blip, but that's actually an airplane, or that's actually a human. And so that's all gathered up and forms some sort of something that indicates that this is an object. It's not just a flash on the screen. And then cognition models will go to those models that have figured out what was detected, and then get that information out of the equipment models, and then make decisions based on that. So that's exactly what's happening here. We have a very simplistic representation of a radar model, and that's what this is right here. And it has an antenna height, and we'll talk about antennas in a minute. It has a scan period, which is what's the period at which it goes out and basically takes a snapshot of the things that are around it, and then a maximum range. So it can only see things, in this case, within 10 kilometers. And then there's a little checkbox here that says whether or not terrain is going to be considered. So without terrain, if that box is not checked, we will see everything regardless of whether it's on the other side of a hill or not. If we check that box, then terrain is considered. And we do that so that you can see in the source code to the sensor model how you call the terrain models to do terrain masking calculations. And if it is masked by the terrain, then it won't see it. So that's what this sensor model does. Every 3 seconds it goes out and looks at all the things around it based upon this geometry and whether or not terrain is there. And then it feeds each snapshot of each set of detections to a tracker model, which is this data processor model. So this particular sensor model is actually a composite model. It has its own model, plus it has two other models attached to it, a data processor model and an antenna model. So a data processor model is not necessary for all types of sensors. If you have an imaging sensor that a human looks at directly, you don't necessarily have a tracker. You could if you had it, but if it's a set of night vision goggles, the human brain is the tracker, so you wouldn't necessarily have a data processor. But this is intended to simulate a radar. So radars almost always have something that takes successive measurements from the radar and tries to build a track out of it. So it correlates measurements over time to say, well, this is an airplane or this is something else that's moving out there. So that's done by a data processor model. And in Flames, a data processor model is just a model of a computer. And it doesn't have to be used for sensor time-dependent processing. It could be used for anything, because in the real world, there are all kinds of computers. So we have a data processor that we use for performing track processing. So I can go browse to that. We only have one of them here. It's called the FEX tracker. And all it has in there is how frequently it sends messages. So this data processor, like real trackers, has the ability to send messages to other systems and get messages from other systems and merge that track data and correlate it in to form an air picture or a ground picture that is based on the data that it sees with its own sensor plus the data that it gets from other sensors. So that's built into this data processor. And that's another thing that data processors do, is they oftentimes will perform communication. And then it has this purge interval, so if we haven't seen an object in more than 20 seconds, then we'll just throw the track out. So it's very, very simple. And again, you can see the source code for that. So we specify which data processor we want to use, and we also specify what antenna. So sometimes sensor models don't have antennas. If it's an infrared sensor and it's, say, night vision goggles, there wouldn't be an antenna, but a lot of sensors do, and radars in particular, they'll have some sort of an antenna. This antenna model is very, very simple. It's based primarily just on geometry, but in order to show our customers how to build sensor models that use data processors and use antennas and how those models interface with each other, we put a very simple antenna model in it. So this antenna model just has a constant gain, a main beam gain and a main beam width. And we use those values in the calculation, but very, very simple. Basically, if this sensor, these gain values are really only used when we're doing jamming. And we'll talk about that when we go to jammers, but we don't really use the antenna. We just use the range of the sensor as our primary means of determining whether we detect something. That's the primary thing that we use. But we use that antenna when we're doing jamming calculations primarily. So we'll talk more about the antenna later. But the sensor models, the radar models that are in the starter models are more complicated. We're actually using the radar range equation, and we're using still noise ratio values and signal thresholds and a bunch of other stuff. And so we illustrate how those types of models interact with each other with this model. So we're just going to go attach this sensor now, and we're going to do it the same way that we attached any other type of sensor. We'll go to our unit, we'll go to its script, and we will put another employ statement in. So you can kind of guess what I'm going to say right here, employ, and I'll say sensor, and then I'll pick a sensor meta object, and I only have one, and I'll put semicolon there, and I hit accept. And so now I go to my composition, and you're going to see I get 3 models attached to this unit. The sensor itself, so it got cloned, and then the sensor referred to meta objects here of a data processor and an antenna. And this, when this sensor got cloned to be employed by the unit, these particular meta objects that are referenced here, they also got cloned. So 3 total models got cloned, and they are attached to the unit so that the sensor has its own local pointers to those objects, but there's also pointers directly on the unit to those models, so you can see them all right here. Let me talk a little bit more about the subsystem model, this antenna. So I'm going to go to this window. The antenna is a subclass of subsystem. And subsystem is a sort of a generic class. It doesn't really have any specifically defined role in Flames, but But we know that a lot of real-world systems are themselves formed of multiple parts. And so this allows us, if we choose, to model the individual parts of an overall larger system individually, and then be able to have additional specific parameters that we enter for those individual parts, and to be able to compose our overall system by mixing and matching different kinds of antennas. So I've got, I think, 2 other antenna classes in the starter model. So, and those are compatible with a lot of different kinds of sensors. So I can use a high fidelity antenna or a lower fidelity antenna. And so I can swap out which particular kind of antenna model I use. I have different kinds of trackers, so I can swap those out. And as long as they support the right interfaces, I can implement different kinds of models. I can take models that are written by somebody else and use them along with my sensor model. So subsystems give me the ability to do that, to break a system up in pieces and then be able to model those pieces separately and swap them out. So for example, if I was modeling a tank, I might put the engine as a subsystem. So I could put bigger engines or smaller engines inside of my tank. So I could use a subsystem anywhere I want, whenever I want to break a system into pieces. And since that's a fairly common thing, we have that subsystem class. In our models, we don't have any other subsystem models except antenna models in the starter models, but they're there to show you how you could use that for other purposes. So again, back to the unit, when I employ that sensor model, this with this statement right here, it automatically clones 3 models and they all get attached directly to my unit. I've already talked to you about the overall flow of a sensor model. Sensor models are called in a time step fashion. Cognition models are called in all event-based, but sensor models are called in a time step fashion. So in this particular case, even though the sensor might be called a lot more frequently, the actual scan of a sensor is specified here every 3 seconds. So even though we might say be running at a 1/10 of a second time step, the sensor won't do anything for each 1/10 of a second until it's been 3 seconds since the last scan. And then it'll go out and detect everything around it and pass those detections on to the data processor. What happens with those tracks that get formed by the data processor is they get stored in the data processor, and then a cognition model attached to the unit will go out and get those tracks and then use those tracks for making engagement decisions. And those tracks will also be sent via messages to other units. So we really can't see that yet because we don't have a cognition model on here that's even going to look at the sensor. Our ground vehicle driver doesn't do anything with sensors or data processors. It only works with the platform. So just like when we put the platform on, if we don't have a cognition model that uses it, it's pretty much useless. The same is true for the sensor. It's going to be gathering up detections, but those detections are not going to be useful. But even though that's the case, I'm going to put something in this scenario that this sensor model can detect. Now, in fact, I'll wait till the next video to do that because this video is getting kind of long. So that's an overview of sensors and the extremely important role that they play in a flame simulation. I'm going to end this video now, and we're going to add another cognition model to this unit that actually looks at the data that's associated with the sensor. But before we do that, we're going to actually add a couple more models to this unit so that once we detect something, we can actually shoot it. So stay tuned. I look forward to talking with you in the next video. Thanks for watching, and thank you for using flames.